For centuries, humanity has sought to unravel the mysteries of the cosmos, each new telescope revealing more of the universe's secrets. Today, the James Webb Space Telescope, JWST, is our most powerful tool yet, a golden mirrored marvel that sees the universe in infrared, peering through cosmic dust and back in time. JWST's mission: Media Group, JWST in orbit with deep space background, animation of JWST starting its mission, JWST launching into space at its dock and at distribute_equally, to witness the birth of the first stars and galaxies, study how they evolve, and search for the building blocks of life on distant worlds. Recently, astronomers turned this extraordinary eye toward the heart of our Milky Way, targeting its supermassive black hole. What Webb found there is rewriting everything we thought we knew about these cosmic giants. So, what exactly is a black hole? It's one of the most mysterious and fascinating objects in the universe, a place where the laws of physics as we know them seem to break down. Black holes have captured the imagination of scientists and the public alike for decades, and for good reason. It's a region where gravity is so intense that nothing, not even light, can escape. The gravitational pull is so strong that it warps the very fabric of space and time, creating a cosmic trap from which nothing can return. This happens when a massive amount of matter is squeezed into a tiny space, warping space-time and creating a point of no return: the event horizon. Imagine compressing a star several times more massive than our Sun into a sphere no bigger than a city. The result is a gravitational well so deep, not even light can climb out. Once anything crosses this boundary, it's lost forever, pulled toward a singularity of infinite density. The singularity is a point where all the black hole's mass is concentrated, and where our current understanding of physics simply breaks down. We can't see inside a black hole, but we can observe its effects on nearby stars and gas. Stars may orbit an invisible point, or clouds of gas may swirl and heat up as they're drawn in, revealing the black hole's presence through their motion and energy. Matter spirals into the black hole, forming a superheated accretion disk that glows across the electromagnetic spectrum. This disk can reach temperatures of millions of degrees, emitting X-rays and other high-energy light that we can detect with telescopes. This disk is where the action happens. Gas and dust heat up, emitting light just outside the event horizon. The intense friction and gravity create spectacular displays of energy, making black holes some of the brightest objects in the universe despite their dark centers. By studying this light, astronomers can deduce the black hole's mass, spin, and the extreme physics at play. Observations of these glowing disks and the motion of nearby stars help us unlock the secrets of these invisible giants. Black holes aren't just cosmic vacuum cleaners, they're dynamic engines shaping their surroundings. Some even launch powerful jets of particles at nearly the speed of light, influencing the evolution of entire galaxies. The accretion disk's light is our window into these invisible monsters. Without it, black holes would be almost impossible to detect, hidden in the darkness of space. With JWST, we can now study these regions in unprecedented detail. Its powerful infrared vision allows us to peer through dust and gas, revealing the secrets of black holes like never before. Let's see what happens when we point it at our own galaxy's core, where a supermassive black hole lurks at the heart of the Milky Way, waiting to be explored. At the Milky Way center lies Sagittarius A, a supermassive black hole with the mass of 4 million suns. The galactic core is shrouded in dust, making it nearly impossible to observe with visible light. JWST's infrared vision cuts through this dust, offering the clearest view yet of Sagittarius A's environment. Scientists used Webb to conduct the longest, most detailed observation of this region, 48 hours of near-continuous monitoring. They expected to see a mostly quiet black hole with occasional flares. Instead, Webb revealed a scene of constant, restless activity. The accretion disk was alive with rapid flares and flickers, no periods of calm. Sagittarius is not a dormant giant, but a cauldron of ceaseless energy. This discovery forces us to rethink the very nature of our galaxy's heart. Picture a campfire, never still, always flickering. The flames leap and dance, casting ever-changing shadows, never repeating the same pattern twice. This restless energy, this constant motion, is mesmerizing to watch. That's what Webb saw at Sagittarius, the supermassive black hole at the heart of our galaxy. But instead of fire, it's light and energy, flaring and fading in a cosmic dance. Instead of rare outbursts, the black hole's surroundings were in perpetual turmoil. Major flares erupting unpredictably, countless subflares sparking in between, each one a burst of energy from matter spiraling inward. And in the background, a steady stream of faint flickers, tiny pulses of light that never seem to stop, as if the black hole is constantly simmering with activity. On an average day, Cygare* produces 5 or 6 major flares, each one unleashing tremendous energy, enough to outshine the combined light of millions of stars for a brief moment. Beneath these dramatic events, a constant undercurrent of smaller rapid flares keeps the region in motion, like sparks flying from a grinding wheel. The accretion disk is far more turbulent and unstable than we ever imagined. Gas and dust swirling chaotically, colliding, heating up and radiating energy in all directions. Rather than feasting on rare, large meals, Cygare* is constantly snacking on smaller morsels, clumps of gas and dust that fall in, fueling the ongoing fireworks. This relentless feeding keeps the environment agitated, a simmering pot always on the verge of boiling over, never quite settling down. The activity appears random with no clear pattern or rhythm, just a chaotic symphony of light and energy, impossible to predict. This chaos is a vital clue, hinting at complex, turbulent processes at work, magnetic fields twisting, matter colliding, and forces we're only beginning to understand. Understanding this unpredictability is now a central challenge for astronomers. Each flare, each flicker is a piece of the puzzle, helping us decode the secrets of black holes. The heart of our galaxy is far more dynamic, volatile, and alive than we ever dreamed. A place where chaos reigns and mysteries await discovery. Let's focus on the faint flickers, the subtle, persistent background of Cygare*'s light show. These glimmers are easy to overlook, but they hold crucial clues about the black hole's environment. Unlike the dramatic flares that grab our attention, these faint pulses are always present, quietly illuminating the story of what's happening just outside the event horizon. These rapid, small variations are caused by turbulence in the accretion disk, where gas swirls chaotically under extreme gravity and magnetic fields. The disk is a cosmic maelstrom, with matter constantly colliding, heating up and spiraling inward. This turbulence is not random, it's shaped by the immense forces at play, creating a dynamic, ever-shifting landscape. Localized pockets of plasma heat up and glow briefly, then fade, creating the flickers Webb detects. Each flicker is a sign of energy being released as matter is compressed and heated to millions of degrees, before it either falls into the black hole or is ejected outward. This constant flickering is the visible signature of the black hole's feeding process. It's like watching the heartbeat of the galaxy's core, a steady rhythm that tells us the black hole is actively consuming material. By analyzing thousands of these events, scientists can model the disk's density, temperature, and velocity. Each data point helps refine our understanding of how matter behaves under such extreme conditions, and how energy is transported and radiated away. The accretion disk is not a calm flow, but a stormy, ever-changing environment. It's a place of constant upheaval, where new structures form and dissolve in moments, and where the laws of physics are pushed to their limits. These flickers are the weather of the black hole's surroundings. Just as storms and winds shape our planet, these cosmic fluctuations sculpt the environment around Cygare**, influencing how and when the black hole feeds. For the first time, we have a detailed forecast of the storm raging at our galaxy's core. Webb's observations let us peer into this chaos, revealing patterns and cycles that were invisible before. Webb's sensitivity is revealing the fundamental physics of black hole feeding in real time, opening a new window into the most extreme environments in the universe and helping us understand the forces that shape galaxies themselves. The big bright flares are driven by a violent process magnetic reconnection. The accretion disk is threaded with powerful magnetic fields, twisted and tangled by swirling plasma. When these fields snap and realign, they unleash explosive bursts of energy, magnetic reconnection, the same process behind solar flares, but on a galactic scale. This energy accelerates particles to near light speed, producing intense synchrotron radiation, the brilliant flares we observe. A single flare can make Cygare* hundreds of times brighter for a brief moment. Webb's observations give us a front-row seat to one of the universe's most powerful particle accelerators. Studying these flares helps us understand energy release and magnetic chaos across the cosmos. Webb's most revealing discovery was a time delay in the light from Cygare**'s flares. When a flare erupts, The brightness at shorter infrared wavelengths changes just before the longer ones, a delay of seconds to tens of seconds. This delay shows how high-energy electrons cool, shifting their emission from short to long wavelengths. Measuring this effect lets scientists probe the magnetic field strength and plasma density right next to the event horizon. It's like placing a thermometer and magnetometer at the edge of a black hole. This breakthrough opens a new window into the extreme physics at our galaxy's core. Webb is mapping the invisible, particle by particle. JWST has revealed SGRA* as a restless, flickering engine, its activity driven by turbulence and magnetic explosions. These discoveries reshape our understanding of how black holes feed and influence their galaxies. By studying SGRA* in detail, we learn about the universal processes that govern galaxy evolution. Each flare and flicker is a clue, challenging old theories and inspiring new ones. The science team plans even longer, uninterrupted observations to uncover deeper patterns. Black holes remain the ultimate frontier, pushing the limits of physics. With JWST, we're entering a new era of cosmic discovery. The secrets of the universe's most extreme objects are finally within reach.